So, in the laboratory and in industry and in medicine, we're often curious about what we got as compared to what we thought we'd get in an experiment, in a production, in a manufacturing process. Yeah, the topic is yields. Theoretical yield is how much we thought we'd get. The actual yield is what we actually got, really got, measured in the lab. The percent yield is the actual divided by the theoretical. The percent error could be said to be the difference between what you got and what you should have got, or what you got and what you thought you'd get, divided by what you thought you'd get times 100%. Or in other words, the error plus the yield should be 100%. I just typed that up in my little PDF document. It's not very pretty, but it'll work for now. You can rewrite it however you like. Question: if I took 3.98 grams of magnesium and burned it in excess oxygen in the air and plenty of oxygen, how much magnesium oxide would I expect, theoretically? Isn't that a fairly simple, straightforward stoichiometric calculation? Maybe. Let's take 0.38 grams of magnesium, change it into moles of magnesium. The balanced equation says 2 moles of magnesium yield 2 moles of magnesium oxide. So 2 to 2. I always write that out so I keep track of my units and don't forget where I'm at in my conversion and what I'm talking about. Then lastly, I change moles of magnesium oxide to grams of magnesium oxide. Thusly, I'm expecting 0.63 grams of magnesium oxide. Start with, wait a minute, I had 0.38 grams of magnesium. Why do I have more mass of magnesium oxide? Well, is it obvious? Because I'm adding oxygen from the air to the magnesium. I'm expecting increased mass. That's the theoretical yield. But then let's say I go to the lab and measure it, and I actually only get 0.17 grams of magnesium oxide. Man, that's sloppy or wasteful or not even collecting all my magnesium oxide somehow. If you've ever burned magnesium in air, you know that it's very smoky, and those smoke particles are little teeny tiny particulates of magnesium oxide getting up away from us in the air. So only 27%. I got 0.17, I thought I'd get 0.63, move the decimal 2 places, 27%. That's poor yield. Man, if you were making magnesium oxide in the industry, that would be a poor way to do it. You need like 95 or more percent in the lab to be proud of anything. Let's do that also in the context of a limiting reactant question. If you're given two amounts of two different reactants, there's a really good chance you're going to have to determine which one might be extra if they don't tell you. If they're really kind, they tell you it's a limiting reactant question. They might ask what's the limiting reactant. But if I have 50 grams of NO2 and 25 grams of H2O, that's a little confusing. Unless that's exactly coincidentally the right amount to use, I better change both 50 grams and 25 grams to moles, then compare them to each other and also in relation to the balanced equation. So 50 grams of NO2 and 25 grams of water change to moles, molar masses. But the balanced equation says I need 3 times more NO2 than H2O, so this number should be 3 times bigger than this number. Is this number 3 times bigger than this number? Well, as a matter of fact, it's not even bigger, it's smaller. So being less than 3 times more this number, this NO2 is definitely limiting. Since the NO2 is limiting, then I can take that from there in the 3 to 2 ratio to find out how many grams of HNO3 I would expect. 3 to 2 ratio, moles of NO2 cancel, moles of HNO3, change moles of HNO3 to grams of HNO3, 45.8 grams of HNO3 theoretically expected from the stoichiometry. And this, I'm just making this up to save time. What if I went in the lab and actually did it and measured 41.5 grams of HNO3? Well, that's less. You always get less than what you expect, so the percent yield is always less than 100%. And I take what I got compared to what I thought I should have got, or in other words, the percent error is the actual minus theoretical divided by the theoretical, and it comes out to 90.39 or 9.39, 9.4. Add these two together, and lo and behold, you see 100%. Gosh, that is so much fun. Let's try that again. Or you know what? You should try this yourself at some point in your life, at least 3 times. After the third time, you're like, God, this is boring. I understand this too well. But here's a chance, if you'd like, to pause the video. 50 grams of FeO2. Oh no, this isn't a limiting reactant. It's just a straight up percent. So I have excess aluminum. I'm not given two amounts of reactants. I have as much of this as I want. Given 50 grams of this, how much of this would I expect? And if I only got 28.65 grams of iron, this is the actual yield, right? Pause the video if you'd like, and or not, because here's the answer. So 50 grams of Fe2O3 changed to moles. It's a 2-to-1 ratio on the balanced equation. For every 1 mole of Fe2O3, I get 2 moles of iron. Not surprising, there's a 2 there. In any case, change moles of iron to grams of iron. I expect 35-ish grams of iron, but the question was framed with the actual yield of 28.65 divided by the theoretical 0.8193, 81.93%. Interesting. Yay, that's all. Practice with that sometime. You probably already have in the lab if I understand what you're doing in the lab. Thanks, guys. See you soon.